Hi guys, I'm Yuki from External Level Japan at Solana Foundation. On Solana, almost everything an app does, checking a balance, showing transaction history, listing tokens, it's a read. And right now, every one of those reads is crammed into a single RPC node. In this video, we'll look at RPC 2.0, the redesign that rebuilds that read layer, and we'll do it hands-on, playing with the diagrams. There's some jargon, but we start from intuition, so newcomers will be fine. This project is built with the Solana Foundation and open sourced under a license called AGPL. Anyone can use it, but if you run a modified version as a service, you must publish your changes too. It's designed to prevent lock-in, and that idea pays off later. Let's play this. On the left is Agave. Today is one of the Solana's nodes. It runs consensus, state, registrage, and every RPC read, all in one process. Press play and the read lift out of Agave and split into two paths. One answer is what's true now? That's Cloudbreak. And the other answer is what happened before? That's Superbank. Reads move out of the validator and the resource contention is resolved. That's the whole core of RPC 2.0. What's true now goes to Cloudbreak, and what's happened before goes to Superbank. Two fundamental different questions, each with its own purpose-built path. Everything else is the why and the how. So why rebuild it? The first reason is speed. Now, quick quiz. Why is 3-month-old history slow? The answer is B. It was stored in a DB. It's suited to that access pattern. It's not the volume of data. It's how it's stored and fetched. And next, watch this. The tank in the middle is the nodes RAM, I/O, and CPU. One single set of resources. On play, 4 jobs: consensus, accounts, ledger writes, and all reads. These float that one set at once. The tank saturates red, and the read response alone is left waiting. That's contention. Reads are fighting consensus for the very same resources. And all history isn't local. It's a network round trip to big table. Only the reads of all history leaves the nodes, and that's a second source of slowness. Let's see in its numbers. Top is the old way, and bottom is RPC 2.0. Get program accounts GPA, for instance, is roughly 20 times faster on average. And type a method name for a short notice like this: GPA, GSFA, and so on. These are all Triton's own measurements, and the guide is explicit that the multiplier shifts with the baseline. No exaggeration, just source numbers. This is the big picture. Reads get routed two ways. Click a method and the engine that serves it lights up. Current state calls, get account info, get program accounts, and so on goes to Cloudbreak. And history calls, get transaction, get signatures for addresses, get signature statuses, and get block go to Superbank. This routing matches the actual methods implemented in the public repositories. State versus history. The question's nature decides the path. Next, engines. This is the heart of it. What's inside the two engines? History first. Superbank. Superbank isn't picky about the inlet. Whenever the data comes from, it stores everything, unfiltered, and organizes it for the questions people actually ask, so it can answer fast later. There's also an optimal features that answers the most recent slots from memory in under a millisecond, and open the details, and you get the real inlets. Human gRPC, JSON RPC, and Bigtable, plus the 3-table ClickHouse layout and the head cache. Concept first and details on demand. And next, here is the key idea. From one source of truth or transactions, it prepares answers to the common questions ahead of time at right time. This address history, is this signature final, this token's activity. The answers are kept newest first, so history lookups are fast. And expand it for the real tables and DDL. Transactions is the source, and 3 views, GSFL, signatures, token owner activity are bucketed by address, signature, and owner, sorted by slot descending, newest first. That's what fast actually is. And one more. The new method getTransactions for address. Fetching wallet history used to mean list the signatures, then fetch each one, n+1 round trips. GTFA for that into a single request. Resolve server-side, return in one round trip. From n+1 to 1. That's the point. The internals are one expand away if you want them. Now the state side, Cloudbreak. Its showpiece is out indexing. In a line, it counts which questions come often, and for the frequent ones, it auto-builds a shortcut. Let's fire the same query over and over. The query tracker counts, and at 10, it auto-builds a tailored PostgreSQL index. Then watch it. Like this. And then latency just dropped sharply. From now on, this query skips the scan and hits the index directory. No manual setup, no index request. Reset to run it again. The default thresholds are listed below, straight from the official config. Next, trust. Fast and cheap, fine. But is it correct? Does it break? Consistency and self-healing. Another quiz. What if the live stream drops slots? The answer is B. It detects the gap and auto-recovers from incremental snapshots. And step 1. On startup, seed every account from a full snapshot. And step 2. Keep applying updates from a live gRPC stream. And step 3. If the stream drops slots, detect the gap, that's the one in red. And step 4. With no manual intervention, recover from incremental snapshots and restore consistency. And here is the other important bit. Each account keeps only its newest version. Superseded ones are discarded. Garbage collected on finalization. So the data never grows without bond with history, and complete current state is always returned instantly. This behavior is verifiable in the public repos implementation. Then the snapshots themselves come through the cluster tracker and snapshot crate. This one. 1. Ask which pair to use. 2. Download. 3. Unpack. 4. Read the account data. And 5. Bulk upsert just the needed accounts into Postgres. The same path serves both startup bootstraps and gap recovery. Now, the part that explains why RPC 2.0 is open source, fragmentation and lock-in. Let's play it. First, the raw data is open. Anyone can read it, but each provider built its own fastpass inside, behind a closed API. So, an app built around provider A can't switch to provider B. It's lock-in. And an improvement made at A doesn't cross to B. Everyone keeps reinventing the same wheel. This is where AGPL pays off. If you modify it and offer it as a service, you must publish the source, which makes closed fastpass hard to keep and lets improvements flow back to everyone. RPC 2.0 is open source precisely to undo this fragmentation. Finally, where things stand, just the facts. Who benefits? A sole dev can start on a laptop. A large team gets flat cost queries against its own infra. A provider can adopt it without years of R&D, and an institution can audit it end-to-end inside its own perimeter. The history is tidy too. On Answers 2021, Geyser Foundation, Triton built Yellowstone gRPC, and all faithful opened the full ledger. RPC 2.0 was announced in April 2026, and Superbank and Cloudbreak were open sourced under AGPL that June. And the cost is realistic. A full chain fits in about 700 GB on a single PostgreSQL node for under $400 a month, versus $3,000 plus for a dedicated Agave index node. A big difference. That's Solana RPC 2.0, splitting one lead path into current state and full history. This guide is interactive, so please play with it yourself. Thank you for watching. Bye.